So 9.2 is all about angles in radian measure. When we draw angles, we draw them in what's called standard position. So this is a graphic of standard position on the right. So with standard position, the vertex of the angle, that's where the two sides meet, that's at the origin. And then the initial side, or where you start the angle, that's always on the positive x-axis. So the angle always starts right here. You'll always have one line of the angle right there. And then the terminal side, that's where the angle ends. So depending on what the degree measure is, the angle will end in different spots, but the side where it ends, that's called the terminal side. And then positive angles, they're gonna rotate counterclockwise. So if we're drawing a positive angle, we'll start on the initial side and go counterclockwise to get to that degree or radian. And then negative angles rotate clockwise. So we'll still start at that same positive x-axis initial side, but we'll go clockwise instead. So there's going to be times where you'll want to convert between degrees and radians, or you'll be asked to. So in order to convert from degrees to radians, so starting with degrees and then going to radians, you would take your degrees and multiply them by pi radians over 180 degrees, or just pi over 180. And then if you have radians and you want to convert them to degrees, you have to multiply by 180 degrees over pi radians. So for example 1, draw the given angle in standard position. So for 120 degrees, no matter what, it's going to start on the positive x-axis. So we can draw the first part of our angle there, just extending from the origin out to the right. And then for 180 degrees, it's the same kind of like degree measurements as we think of when we think of a circle. So all the way around, it's 360 degrees. If I go up to a right angle, that's 90 degrees. Another 90 degrees, another right angle gets me to 180 degrees. Another 90 degrees, another right angle gets me from 180 to 270. And then another 90 degrees, another right angle gets me from 270 to 360. And you can go around as many times as you want. There's no limit to like a degree measurement. Like we could draw like an angle of 600 degrees. That would just require us to go around a few times. So for 180 degrees, if I'm starting here and I go up to the y-axis, I know that's 90 degrees. If I continue to go down to the negative x-axis, I've gone too far because I've gone 180 degrees. I only want to go 120. So I have to go up to 90. And then after I get to 90, I have 30 more to go to get to 120. So if I have 30 more to go, that's going to be like another third of the way down to 180, because a third of a 90-degree angle is going to be 30 degrees. And these don't have to be perfect, but they should definitely be in the correct quadrant and preferably like closer to the axis they're closer to. The last thing you want to do is you just want to draw an arrow showing which direction that your angle is opening. And then for B, it's 390 degrees. So no matter what, we're starting at the initial side on the positive x-axis. So starting from the origin and extending to the right. And then if I want to go 390 degrees, so if I go all the way around, that's 360 back up to here. And then to get from 360 to 390, I have to go an additional 30. So about another third of the way up. And then just if we have to go past, or if we've gone over 360 degrees, we're not just going to draw like one little arrow on here. We want to show how many times we're going around. And then for C, negative 160 degrees. So same starting point. It's always going to be the same starting point on the positive x-axis. But if I want to go in the negative direction, then I have to, instead of going counterclockwise, I'm going to go clockwise. So if I go clockwise to 90, or to negative 90, that's right here, and then to negative 180, that would be right here, but I've gone too far. So I want to go a little bit less than negative 180. So like I said, it doesn't have to be perfect. It's kind of hard for it to be perfect without a protractor, but just make it as accurate as you can. And then since it's negative, we're going clockwise. So for D, E, and F, those all have pi in their measurement, so that means that they're in radians. So while we're getting used to radians, it's helpful to turn them into degrees so we kind of have an idea of how to draw those angles. So if I want to convert from radians to degrees, I'm multiplying by 180 over pi. So I'm going to take pi, my measurement from D, and multiply it by 180 over pi. And then pi and pi, those cancel each other out. It's like cross-canceling. So we're just left with 180 degrees. So we know how to draw a 180-degree angle. So it still starts on the initial side, the positive x-axis. If I go up here, that's to 90, and then up one more right angle, around one more right angle, gets me to 180. So 180 degree angle is just a straight line. And then for E, we have another radian measure, so it's probably going to be helpful to turn it into degrees while we're getting used to it. So I'm going to take pi over 2. And to convert from radians to degrees, I'm going to multiply by 180 over pi. So then the pi's cancel out. The 2 and the 180, those can cross cancel. The 2 becomes a 1. The 180 becomes a 90. So pi over 2 times 180 over pi is 90 degrees. So it starts on the initial side, the positive x-axis, and then if I go up to 90 degrees, that's just a right angle, so I'm stopping right here. And then I forgot to draw my arrow showing the direction we're going for up here, but you still do want to do that with radians as well. So just showing that we're going counterclockwise. And then for pi over 4, same thing, it's radians. We probably want to convert it to degrees at least while we're getting used to them. So we take pi over 4 and we multiply that by 180 degrees over pi. And then the pi's cancel out. The 4 and the 180 I can cross cancel. The 4 becomes a 1. The 180 becomes a 45 degrees. So pi over 4 times 180 over pi is 45 degrees. So my initial side, and then if I want to go 45 degrees, so 45 is just half of 90. So if up here is 90, I want to go halfway, so about right in the middle of the first quadrant. And then we're rotating counterclockwise because it's a positive angle. So for the next section, it's talking about coterminal angles. So coterminal angles are angles that have the same terminal position, so they have the same endpoint. They're not necessarily the same angle, they just end in the same spot because we can go around in a circle as many times as we want. So an example of a coterminal angle would be 30 and then 390. So if we look, we drew 390 up here. This is the same, pretty much the same drawing we would do if we were just drawing 30 degrees. We just wouldn't wrap around more than one time, we would just go straight up here. But they have the same terminal position, so they're coterminal angles. For example 2, it says find 2 coterminal angles to the following. So if I want to like stop in the same position, like we'll use this example again. If I want to stop in the same position, I have to wrap around the circle one more time to get to that same exact spot. So when we're in degrees, I have to go around another 360 degrees in order to end in the same spot. So in order to find a coterminal angle, you can add 360, and you can add as many 360s as you want. So if you want to continue to add 360 to get to another one, you can, or you can even subtract 360. So as long as for degrees you're adding or subtracting 360, that's going to get you to an angle that stops in the same spot. So for my first one, I'm going to take 120 and add 360. And 120 plus 360 is 480. So that's my first coterminal angle. And then to get my second, I'm going to take 120 and subtract 360. So 120 minus 360, that's negative 240, and it's okay to have a negative angle. Those aren't the only two options though. If I wanted to, I could just take this 480 and I can add another 360. Or I could have started here and subtracted another 360. You can add or subtract 360 as many times as you want, and it's going to create basically like an infinite amount of coterminal angles. And then for example 2, it's 5 pi over 6, so this is in radians. So there's 2 pi radians in every circle. So no matter what, all the way around a circle is 2 pi. So in order to find coterminal angles in radians, we're either adding or subtracting 2 pi. And if you ever forget, remember that you can just like convert degrees to radians as well to check if you're like while we're getting comfortable with it. So if I were to take 360 degrees, that's how many degrees are in that full circle, and multiply it by, in order to go from degrees to radians, I'm going to multiply by pi over 180. And then the 180 and the 360 can cross cancel, so the 180 becomes a 1 and the 360 becomes a 2. So then I'm left with 2 times pi, or 2 pi. And then just in addition to that, like we did up here when we just drew pi, that was 180 degrees. So halfway around is just pi, all the way around is 2 pi. So if we want to find an angle that's coterminal with 5 pi over 6, first I'll take 5 pi over 6 and add 2 pi. It's the same thing as adding 360. But in order to be able to like add these values, this is a fraction, so I need to get common denominators. So if I think of 2 pi as instead of fraction over 6, 2 pi rewritten as a fraction over 6 would become 12 pi over 6. So I'm not changing the value, like 12 pi divided by 6 is 2 pi. Just now I have the common denominator, so now I can go ahead and add those fractions. So 5 pi over 6 plus 12 pi over 6 is equal to 5 pi plus 12 pi altogether is 17 pi over 6. And then we can either continue to add another 12 pi over 6, or we can start with 5 pi over 6 and subtract 12 pi over 6. It's up to you. So I'm going to take 5 pi over 6 and subtract 2 pi, or subtract 12 pi over 6. Those are the same. So 5 pi over 6 minus 12 pi over 6. 5 pi minus 12 pi is negative 7 pi. And then over 6. And then the next thing that we're going to talk about is finding the arc length and the area of a sector. So there's two formulas for arc length and area of a sector. For arc length, it's S equals R times theta. And theta is in radians. Theta is an angle measure. And then area for a sector is A equals 1/2 r squared times theta. And then same thing, theta is the angle measurement and it's in radians. So for example 3, it says a softball field forms a sector with dimensions 180 feet by 180 feet. Find the length of the outfield fence and area of the field. So if we kind of compare these two pictures, get an idea of what it's asking. So a sector is like what's created when you extend to radius. So it's kind of like a piece of a pie. And then the arc length is just the length on the outside of the circle of that portion of the sector, that piece of the pie. It's just like the crust, basically. So if we want to first find the length of the outfield fence, that's going to be the arc length. And then if we want to find the area of the field, that's the sector. And I know you can't see the whole circle, but we could extend this and kind of create a whole circle with a radius of 180 feet, since it's 180 by 180. Okay, so the first thing that we have to do, because the arc length and the area formulas are given in radians, or you have to plug radians in, is we got to convert this. I know it's really faint, but that says 90 degrees. We need to convert that 90-degree angle to radians to figure out what radian angle measurement we can use. So we're going to take 90 degrees, and then to convert from degrees to radians, we have to take pi, or we have to multiply by pi over 180 degrees. So the 90 and the 180, those can cross cancel, so 90 becomes 1. 180 becomes 2. So altogether we have pi over 2. So that's this angle. And that's the theta that we can use in our formulas. So if we want to find the length of the outfield fence, the length of the outfield fence is the arc length. It's that measurement of the distance on the outside of the circle. So we're going to use the arc length formula, which is S equals R times theta. And if we think of this field as like a chunk of, or like a quarter of one big circle, the radius of that circle is 180. It's going to go all the way around 180 feet. So that's our radius. So we know our radius, that's 180, and we know theta. So we're able to figure out what the length of the fence is now. So S equals R times theta. It's 180 feet times theta, pi over 2. And then the 180 and the 2, we can cross cancel there. The 2 becomes a 1. The 180 becomes a 90. So we're multiplying 90 times pi. So S is equal to 90 pi. And if you want, you can get an approximation. You don't have to. But 90 pi would be about 282.7 feet. So S is approximately 282.7 feet for our fence length. And then for the area of the entire field, so if we look back up here, that piece of the circle, like the it's like kind of a triangle, but obviously this is curved, that's our sector. So we can use the formula for the area of a sector. So the formula for the area of a sector was A equals 1/2 times R squared times theta. And again, we know R and we know theta, so we can just plug those in to find the area. So A equals 1/2 times R squared, so 180 squared, times theta, so times pi over 2. And then first we got to square the 180. So 180 squared is 32,400. So 1/2 times 32,400, and then times pi over 2. And multiplication is like commutative, so you can kind of multiply it in whatever order you want that makes sense for you. I ran out of room vertically, so I'm going to go horizontally. But if we take 32,400, we multiply by 1/2, or multiply by 0.5, or divide it by 2, it's all the same thing. We get 16,200, and then I'm going to multiply that by pi over 2, so that would become 16,200 pi over 2. So we can kind of like reduce that by dividing 16,200 by 2. So altogether 8,100 times pi. And then same thing, if you want to get kind of an approximation to get an idea of how big that actually is, you could take 8,000, multiply by pi. That's like 25,400 and almost 47 square feet. Okay, so altogether the length of the fence was about 282.7 feet or 90 pi, and then the area of the field was about 25,447 square feet or 8,100 pi square feet.